So let's talk about DeepSeek. If you've clicked on this video, you're probably already aware of what DeepSeek is, so I won't bore you with a long-winded explanation. But if you want more information, I highly recommend that you check out this blog, which I linked into the description below. In a nutshell, though, DeepSeek is a large language model developed by the Chinese company DeepSeek, which rivals OpenAI's O1 in reasoning performance, but at a much cheaper price. I'm talking much cheaper. And DeepSeek claims it only costs $5 million to train, and it's open source. So overnight, we went from having one strong reasoning model that is closed source, pretty expensive, to thousands if you count the fine-tuned versions of DeepSeek that are already on Hugging Face, that are open source and are much cheaper. This and the pretense that you do not need large amounts of compute and GPUs to train a reasoning level model wiped off about $1 trillion from the US stock market. Now, setting aside short-sighted investor sentiment, I still think we're pretty early in this DeepSeek saga. I've seen folks in the community claim that DeepSeek is lying and that they have access to a lot more compute than they claim. I've seen others discuss that DeepSeek is pretty legit. And I've even seen news of OpenAI claiming that DeepSeek used something called knowledge distillation to steal the outputs from OpenAI's models to make DeepSeek models smarter. So we're still pretty early in the story here. We still don't really know what's going on, so I'm not going to pretend that I have a strong take here. What I do know, though, is that we have access to a pretty cheap, strong reasoning model that we can fine-tune right now, which is what we're going to be doing today. Now, my focus throughout the video will be to give you as much intuition as possible over the fine-tuning process. So if you have basic understanding of Python, machine learning, and a bit of knowledge of deep learning, I hope that this should be accessible enough. For me, success in this video is that you walk away not necessarily understanding the math that's going on behind the scenes, but you have a basic understanding of the intuition in plain English of the fine-tuning steps that we're doing today. Just a quick one, today's video walkthrough is a fork of Abid Ali Awan's written tutorial on the same topic on the DataCamp website. Without him, this video would not be possible, so make sure to give him a shout out and check out his blog below. Now with that said, let's get started. So I have a slide here that I'm going to walk you through a bit of the intuition of what we're doing today. DeepSeek is essentially a large language model, so today we're going to be fine-tuning an 8 billion parameter version of DeepSeek, and essentially this is a really rudimentary representation of probably what DeepSeek looks like behind the scenes, and essentially it's a large language model that takes in that has many hyperparameters, many weights, and takes in as input a prompt and returns an output. And what we're going to be doing today is that we're going to be fine-tuning it on a medical data set so that its outputs are much more consistent in the style that we want them to be and more accurate on medical reasoning data. We're going to be fine-tuning DeepSeek on the medical O1 reasoning dataset. We're going to take a look at the dataset shortly, so don't worry about that right now. And we're going to be using a technique called LoRA. For short, it's a low-rank adaptation, so LoRA for short, to be able to fine-tune DeepSeek in an efficient manner. Now, I'm going to give you a bit of intuition for LoRA. I'm not going to go into the math behind it, but maybe I'll use an analogy here. You know, I'm a gamer. I love playing PS5 games, and this is a factory that Sony owns that creates PlayStation 5s. And as you can see, it's really well optimized for creating PS5s. And on the right hand side, I want you to think that we're looking at the factory from a bird's eye view, and each small circle or square here is a node optimized for doing one part of the supply chain. You know, here we attach the GPUs, here we attach the CPUs, here we attach the ports, so on and so forth, right? And this is a factory that is really optimized for building PlayStation 5s. But lo and behold, a few months ago, Sony announced the PlayStation 5 Pro. And now Sony has a pickle on its hand. It needs to optimize its factories to also create PS5 Pros. So you have two options here potentially. The first option is completely change the factories so that they're only optimized for building PlayStation 5 Pros. Now, the con here is that this is really expensive. It takes a long time. and we still want to be able to make PS5s. So changing an entire factory to create from product A to product B is quite expensive and time consuming. The pros, though, is that by the time this process is done, this factory will be extremely good at creating PlayStation 5 Pros. Now, another way that you can do this is part of the factory that matters really, right? Because the PS5 Pro has really similar components to the PS5, it becomes more optimized for building PlayStation 5 Pros. Now, the cons here is that this factory may not be as good at making PS5 Pros as the first one, maybe not be as efficient or fast at making PS5 Pros, but it's pretty cheap to change your logistics. It does not take a long time, and this factory is still able to make PS5s. In a lot of ways, this is what low rank adaptation does. It does not fine-tune all of the weights in a deep learning model, but what it does, that it fine-tunes some of the weights that matter and some of the layers that matter to be able to improve the performance of a large language model on that particular set of data that are included in the fine-tuning data set. Now, I linked here, we're going to link this in the description, a technical explanation of low-rank adaptation by Sebastian Rashka, who is really one of the best NLP researchers in the game. Highly recommend that you check out his content there. But this is the intuition of LoRA, and I won't really be going into the math behind LoRA today in this video. Now, the packages that we're going to be using today are Unsloth, which is a module that allows for efficient fine-tuning and inference of large language models. Of course, we're going to be using Hugging Face because of all of its helper functions to download the data, that fine-tuning data set, download the model, so on and so forth. And we're going to be using weights and biases for tracking our experiment and seeing how it performs. So with that, let's get started. Now, we're going to be using Kaggle notebooks here today. Kaggle notebooks let you use GPUs for free. I think you get around 30 hours a month. So we're going to be using it today. And to be able to set up your GPUs, all you need to do is go on to Settings, go to Accelerator, and choose GPU T4 times 2. All right. So again, as I mentioned, what are the tools and packages we're going to be using today? We're going to be using Unsloth, which is for efficient fine-tuning and inference. Specifically, we're going to be using these two modules, fast language models and get PEFT model. I'll explain these in a bit. And PEFT, what it allows us to do is to allow to adapt the model for low rank adaptation. And we're going to be using a few different Hugging Face modules. So transformers to work with the fine-tuning data and handle different model tasks. Transformer reinforcement learning from Hugging Face allows for the fine-tuning process. And then datasets lets us fetch the reasoning dataset from Hugging Face. And we're going to be also using PyTorch for a few helper tasks, as well as weights and biases for tracking the experimentation. Now, before we get started, we need to have access to Hugging Face and the Weights and Biases API. So again, as I mentioned, first set your GPU accelerator by going on Accelerator and choosing GPU T4 times 2. And then to get a Weights and Biases API, all you need to do is go to the Weights and Biases website, sign up if you haven't, then go to your settings. So I'll go here. And then all we need to do is go to settings, and then you will need to go on API keys, reveal the API keys. You'll be asked to sign up, and then you'll have access, sign in again, sorry, and then you'll have access to the API keys. So going back here. Now, in order to get your Hugging Face tokens, all you need to do is go to Hugging Face as well, sign up if you haven't, and then go to the Hugging Face profile that you see on the top right hand side, press access tokens and go on access tokens, and then you're good to go. I have my access token here already created. All you need to do is copy paste it, and then in the Kaggle notebook interface, you need to go to add-ons, go to secrets, and then add your Hugging Face tokens and your weights and biases tokens. So all you need to do here is press secret. This is the name that you give it. So here I'm using HF_token and WMB, and then you're good to go. Now, I'm also going to begin the process here by installing a few relevant packages. So I'm going to install Unsloth and the latest version of Unsloth here. I'm going to import all my relevant packages throughout this walkthrough. So again, from Unsloth, I'm going to import fast language model. Don't dwell a lot on the packages and the modules that we're using. Just treat these as tools. It's fine if you're not an expert in any of them. We're going to be learning along the way. We're going to import PyTorch from transformer reinforcement learning. We're going to import the SFTT trainer, which is supervised fine-tuning trainer. From Unsloth, import is bfloat16 supported. So this just checks if the hardware they're using supports bfloat16 precision data types. Again, don't dwell about it. It's just a data type technicality here. From Hugging Face Hub, import login. This lets you log into the API. From Transformer, import training arguments. This lets us define the training hyperparameters for the fine-tuning process. Again, we'll check this out. Don't worry about it. From datasets, import load dataset. This lets us load the fine-tuning dataset that we're going to use. And we're going to import weights and biases. And then we're going to import Kaggle secrets from user secret client. So I already ran this code here, right? And you can see here, Unsloth has been imported successfully. Now, one thing, we're going to create the API keys and log in to Hugging Face and weights and biases. So we have this code here that you can see, right? From Kaggle secrets import user client, and then we define a user secrets module. User secrets, sorry, a variable. So we're going to initialize the user secrets variable using the user secret client function. Again, this is from Kaggle secrets, right? We're gonna create the Hugging Face token by get the secret HF token. Again, we're using the same name of the tokens that are here, right? So that's all we need to do. And then we log into weights and biases as well. So I log into Hugging Face token here, right? So we're logged into Hugging Face. And then for weights and biases, I'm going to log in, but then I initialize a new project called Fine-Tune DeepSeek R1 Distill Llama 8B on Medical Chain of Thought Dataset YouTube Walkthrough, short name. And then job type equals training. So we're going to do a fine-tuning process, and then anonymous equals allow. And that's essentially lets us log in here to weights and biases and Hugging Face. Now I've already logged in here just to avoid running code too many times. So with that, let's get started. And the first step that we're going to do here is we're going to load DeepSeek and the Tokenizer, right? So we're going to use from the fast language model module from Unsloth, we're going to use the from pre-trained function, right? And we're going to also configure a few key parameters for inference and fine-tuning, right? So just to explain, what are we doing here? We're going to set the max sequence length, right, that the model can handle, as in the number of inputs it can take to 2048. This is usually canonical here. We're going to set data types to none, so d type equals none, because then the model will be able to auto-detect the data type. And then this is really important. We're going to set to load in 4-bit equals true. And this enables 4-bit quantization. So this is a memory saving optimization technique. Now I want you to give a bit of intuition on 4-bit quantization. You know how you compress images from like 30 megabytes to 4 megabytes without necessarily losing a lot of the quality, but it's compressed? This is what we're doing here, right? So we take the model weights, instead of using a 32-bit or 16-bit numbers, we compress them into 4-bit values, right? So this allows the large language models to run more efficiently on consumer grade GPUs, right, without needing massive amounts of money. And that's essentially what 4-bit quantization is doing here. So what I'm going to do, I'm going to first define the model and the tokenizer. So as you can see here, and the solution code will be available to you. You don't need to worry about necessarily going along, but if you want to get the intuition, you can get this here. I'm going to write fast language model from pre-trained. All right, I'm going to open this here. Model name, I already have this here on my notes. It's Unsloth DeepSeek R1 Distill Llama 8B, make sure capital B. And this essentially is the model that we're going to be using today. It's a distilled version of DeepSeek R1 that is 8 billion parameters. So it's a smaller version of DeepSeek R1. I'm going to set my max sequence length to that same parameter that you see here. The D type is equals to D type. So the data type is set to default, so I'm setting it to none, right? Do I load in 4-bit? Yes, I do load it, so it's true. I enable here 4-bit quantization, right? So I'm gonna take it here. And what is the token? I'm downloading this from Hugging Face. So this is a wrapper function around the Hugging Face function that lets us inference the model and run the model using Unsloth, right, at a much faster pace, right? It's much more efficient. And what I'm going to use here is my Hugging Face token, right? And then I'm going to run it. Let's see if it works. Okay, so I think, yeah, we're downloading the model. It's going to take a few minutes. So we're good to go. I think the tokenizer is there. The model is there. Now, what we're going to do is test the R1 model without any fine tuning on a medical use case, right? So first, we're going to define a system prompt because this includes like placeholders for the instructions, the question we're asking, and the response. And we're going to guide the model to think step by step. Now, if you see here, this think tag, this is the chain of thought. So what makes DeepSeek R1 and O1 special is that these models have a chain of thought. They think before they perform tasks. So we're going to see the chain of thought in action. So I'm going to define a system prompt here. And this prompt will guide the model to think step by step and like provide a logical, accurate answer. And we're going to be running inference on the model. So we're going to be asking it a question and it's going to be giving us a response, right, by providing it a medical question, right? So first, we're going to define the question as you can see here, right? So this question is, a 61-year-old woman with a long history of involuntary urine loss during activities like coughing or sneezing, but no leakage at night, undergoes a gynecological exam and a Q-tip test. Based on these findings, what would a systometry most likely reveal about her residual volume and detrusor contractions? Now, I cannot answer that question, so don't expect me to know the answer to that question, right? But nevertheless, we're just using this for illustrative purposes. Now, first thing that we're gonna do here is I'm gonna maybe first explain the process, right? We're gonna define a test question, right? Then we're gonna format the question and using the structured prompt style, right, that we discussed. And then we're gonna tokenize the input, so get the input in different tokens and move it to GPU for faster inference, right? And then generate a response using the model and then decode the output tokens back into text, right? So to obtain a final readable answer. So going here, first I'm gonna enable optimized inference for Unsloth. So I'm gonna do fast language model, for inference. I'm gonna define model here, right? So unmodel, for inference, like I think Unsloth is faster by 2 times than Hugging Face, right? And since here we already defined the model, we can use the model here, right? So that's step 1. Then step 2, I'm gonna format the question using the prompt style that we have, right? So that it takes in immediately. So this is gonna use the tokenizers here that we created. So inputs equals tokenizer prompt style format question. Okay, so here what I'm doing is I'm just formatting the question according to the prompt style, right? And then I'm gonna make sure that we return PyTorch tensors, right? And that we we convert the input to PyTorch tensors here. And then what I'm gonna do is I'm gonna set 2 equals CUDA so that we move this inference to GPU here. Now, I'm gonna here generate a response right now. So the output is model.generate, right? Which is great. So what is the input that we're using? It's the input that we defined above. So input IDs, first let's define that, equal inputs dot input IDs, right? So here we're these are the tokenized input questions, right? Then attention mask equals inputs dot attention mask. this is just for the model to handle like padding or like empty data here. So don't really worry about this here. This is just, you know, one of the one of the parameters that we need to adjust. Max new tokens equals 1,200. So this limits the response to 1,200 tokens here, right? And then I'm gonna use cache equals true, and what this allows you to do is enables caching for faster inference. So if we use the same question again, it will be able to respond again much more quickly. So now we're gonna decode the response. So response equals tokenizer batch decode equals outputs. Okay, and then what I'm gonna do here, I'm gonna print response. Okay, so again, what we're doing here, we're decoding the outputs, right? Using the tokenizer into our response, right? And if I look at here, the response will be essentially a key value pair. So if I just do print response, oops, what is the error that we have? Oh, we have return tensors. We did a, I think return tensors. Okay. So if I print the response, it will be a dictionary. Okay. So it's actually a list. Sorry about that. And then you can see that we have quite a lot of the text is pretty hard to understand. So what I just need to do is first get the element of the inside the elements of the list, and I'm gonna split it on response. So if you go here, you have question, right? And here is instruction. And then if I go down, you see a think tag. Where's the response? Should be somewhere here. Yeah, it's over here. Sorry about that. So the response is here. And then if I'm going to run this again, it should run more quickly now since we did use cache equals true. So let's see how it performs. Oh, I made a mistake here. I forgot to get, yeah, I should have added here this one. So I'm going to actually, so we don't run this again, I'm going to run this here. And yeah, so you get, because we split on the response, right? And essentially what we need to get is the second element of the list, which is the actual response itself. Since we split on the list here that you can see. Cool. So now we have the response, right? So you can see the chain of thought. Okay, I'm trying to figure out what system it shows off. Let's start breaking chats of history of voluntary urine laws. Yada, yada, yada. DeepSeek is very verbose, as you can see, when it's in a chain of thought, right? And then provides an answer here. This is the most likely revealing increased residual volume in their bladder. This is due to incomplete emptying, so on and so forth. So we now need to fine tune DeepSeek. So why are we even doing that, right? Because it delivered a successful chain of thought and it provided reasoning before the final answer. So if you see that, you know, the reasoning process here, one is really long-winded, so we want it to be a bit more concise, right? And more importantly, we want the final answer to be consistent in a certain style. So with that, let's do a bit of work here to start fine-tuning step by step. So let's get started. You know, if I look at here, step one, which is updating the system prompt, right? So if you notice before we didn't have the end think tag that we had here. So we're gonna first add that to the ending think tag. So we're just gonna add slightly the ending think tag for that we have a third placeholder in our fine-tuning data set for the chain of thought column, right? So all we need to do here is initialize this train prompt style variable, and it will be much clearer once you take a look at the training data set. Now I'm gonna download the fine-tuning data set that we're gonna be using. So if you look at here, this data set that we'll be using today from Hugging Face essentially has 3 columns: a question, the chain of thought associated with the question, and the response, right? You can see here. And this particular data set was used to fine-tune a model called Huatuo GPT-R1, which is a medical LLM designed for advanced medical reasoning. If you want to cite the authors that you can see here. Now, the dataset was constructed using GPT-4o as well, but has been verified for medical problems and accuracy. Now, what we're going to do here is first we're going to download the dataset, right? So I'm going to create dataset equals load underscore dataset. So the name of the dataset is called, I'm just going to copy paste it here, Freedom from Intelligence slash medical 01 reasoning SFT, right? We're gonna specify the language to English, so EN, right? And I'm gonna do split train 0500. Now what this does, it just lets me get the first 500 rows of this data set, and I'm just gonna add this parameter here of trust remote code equals true, which just lets me download the dataset and from remotely, and then I'll put here dataset. As you can see, we're downloading. It's generating the train test split, right? And it's essentially here this dictionary of dataset features, question, complex chain of thought, response, so on and so forth, right? Now, if I want to see the first entry, the second entry of this dataset, I'll just do dataset brackets 1, right? So the question here, a 45-year-old man with a history of alcohol use who has been abstinent for the past 10 years, so on and so forth, right? Complex chain of thought, and then the response that you see here below, right? So the next step is I want to structure the fine-tuning dataset according to the train prompt style that we defined here. So instruction, question, response, chain of thought, and then response, right? So this is something that's quite important because then each question is paired with a chain of thought reasoning and the final response, right? It ensures that every training example that the model sees follows a consistent pattern, which helps in performance, right? And then it helps the model from continuing beyond the expected response by adding the end of sequence token. So I'll define what the end of sequence token here is. It's pretty simple. So EOS token, right? So by the tokenizer has this attribute EOS token, and I'm gonna define it here. It's just essentially a tag that says end of sentence. Don't generate any more content, right? Then I'm gonna define the formatting function. So what this does is that it defines the data set that you just saw here according to this prompt style. So we're just doing a bit of data manipulation here. So define prompts func, right? So what this function does is that it takes as input the examples from the data set that we have. We're going to define an inputs, right, which is essentially the input for the model, right? So from examples, we're going to take the question, right? And again, the question is this, right? A 45-year-old woman, and then we're going to take the complex chain of thoughts. So chain of thoughts here, I'm going to define it into this variable. And I'm going to do complex COT. And then outputs, I'm going to also, and I think it's response. Okay, perfect. So here, for every single example that we get its question, we get the complex chain of thought, we get the response. And what I'm going to do is I'm going to create an empty list called texts to store all of these into one single prompt style format. So what I'm going to do is I'm going to iterate over the data set and then format each question, reasoning step and response according to this prompt style that you see here, and just put it in text. That text list that you saw here, right? So I'm going to zip my inputs here. So for input, chain of thought, and output in zip inputs, chain of thoughts outputs, right? So I'm zipping each example here, right? And then what I'm going to do is I'm going to format. So as you see here, I have the different inputs, right? I'm going to format the inputs according to, so I have the question input here, the think input here, and the response input here, right? I'm going to format them into this style of prompt. So prompt style dot format input chain of thought output plus the EOS token, so the end of sequence token that you see here. So again, what I'm doing is that for each input, the input gets formatted here. Then for each chain of thought, the chain of thought gets formatted here. And then for each response, the response gets formatted here. And then I'm adding at the end an end of sequence token, right? And what I will do is then I will append this text to the text list that I've defined. Okay. And then what I'll do is here return texts, right? And this really returns the, oh, I need to create the key value, name the key here, right? And then, right? So here, hopefully this is correct. Let's test it out, right? I'm going to create a new function called dataset fine tune, and I'm going to map the function that we just created to the dataset. So map formatting prompts func. I'm going to set batch equals true so we can do it in batches, and then dataset fine tune, right? We should have a new text key here, right? And I'm going to set first, right? So yeah, we can see here it is correct. Below is an instruction that describes the task paired with an input, so it's not. Write a response set appropriately. Question, this is the question that we used in the original example. Then response, think tags, and then here is the response, okay, with an end of sentence sequence. Now what we need to do is setting up the model using low rank adaptation, right? So again, I added an intuitive explanation here of low rank adaptation. And essentially what low rank adaptation does is that instead of modifying all the weights of the model, it adds small trainable adapters to specific layers, right, of the model. So again, go back to that PlayStation example. Instead of rebuilding the entire factory to produce a new product, it adds small specialized nodes in the supply chain to existing machines. This allows to adapt quickly without disrupting the core structure, right? Below, we're going to be using the getPef model function, which stands for parameter efficient fine tuning, right? This function, what it does is that it wraps the model, right, with LoRA modifications, right? So again, don't focus on the jargon here. What this model does is it just lets us. What this function does is that it just lets us adapt the model in specific layers of the model. So what I'm going to do is I'm going to create a new model called model LoRA, and I'm going to define from fast language model. So again, if you remember, right, we imported from fast language model geft from unsloth, and I'm going to use the getPef model function. Again, the input here, the first one, is our model. So we're wrapping this model up with LoRA modifications. We're going to set R equals 16, right? This determines the number, the size of trainable adapters. So the higher means we're adapting more weights. The lower, we're being more efficient, right? So I'm going to use 16 here after some trial and error, right? And then I'm going to define which layers the LoRA adapters will be applied to. So again, I won't go into the math here, but highly recommend that you check out our transformers content and blogs and courses. I link to them in the description because here what we're going to be doing, we're going to be defining a list of specific layers in the transformer architecture of DeepSeek that we will be adapting. So here, QProj is the query projection and the self-attention mechanism. We have KProj is the key projection in the self-attention mechanism. Again, I don't want to go through the math. These are essentially target modules from the attention mechanism, and it's essentially different parts of the transformer architecture that we are adapting here, right? VProj, which is the value projection in the self-attention mechanism. Again, highly recommend that you check out the tutorials on these. OProj, which is output projection from the attention layer. And then GateProj, which is the feed forward layers here. UProj, this is part of the network's feed forward, the transformers feed forward network. And DownProj, another part of the network's feed forward, of the transformers feed forward network, right? And again, I'll repeat here, what we're just doing here is listing the transformer layers where LoRA will be applied. That is what we're doing. The solution code is much more commented. You'll be able to check it out as well, step by step. But for these, highly recommend that you check out, a transformers architecture tutorial to be able to get an understanding of what we're actually doing here, right? The intuition, though, is that we're just adapting some parts of the factory, right? And we're defining what these parts are. Now we're gonna set LoRA alpha equals 16, right? So here, the higher this number is, the more weight changes the LoRA process will do to these layers, right? So LoRA dropout, we're gonna set equals 0, right? So this means no dropout. Dropout means essentially how much information you retain in the weight updating process. So here we're setting full retention of information, right? Bias equals to none, right? This specifies whether the LoRA layers that we're updating should learn bias terms, right? So this essentially is a memory saving technique, right? So here, this is another unsloth memory saving technique. Grading checkpointing equals unsloth. Okay, so this saves memory by recomputing the activations that we're doing instead of storing them. And this is especially useful for fine-tuning on long data sets with long context. I'm going to set random state equals 347. So this is for reproducibility. This is a random seed. And then that's essentially it. So use RS LoRA. So this is a technique of LoRA called rank stabilized LoRA, right? So I'm going to set this as false. I'm not going to go into the details here. Just set this as false because this essentially goes beyond the scope of today's discussion on what low rank approximation is, adaptation is, sorry. And then, so I'm going to set this as well. Loft config equals none. And this is low bit fine tuning quantization. So we've disabled this because we already have 4-bit quantization. Now let's see if this works here. Okay, we have gotten it done. Now what we need to do now is specify the fine tuning process, right? So we're gonna initialize the fine tuning trainer that we've gotten from Hugging Face's SFT trainer. So if I go up here to my imports, we're gonna be using this function SFT trainer from transformer reinforcement learning. So with that said, let's get started, right? So we're gonna define a trainer object, right? And we're gonna again use the supervised fine-tuning trainer function. The model that we'll be using is this low rank adapted model. So model LoRA, right? Then the tokenizer equals the tokenizer that we've already defined. So this is the tokenizer to input the process the text inputs. Oops, right? The training data set, right, is the data set for the fine tune that we've already defined previously, right? What is the field that we're going to be using as training, which is this text field, right? So data set text field equals text, right? What is the max sequence length? Sorry about that. That's already defined from our previous inference when we did the inference pre fine tuning. So the max sec length, which is I think 2048. What is the number of processors to use to process the data, right? So I set 2 CPUs here. And then what I'm going to do is I'm going to define the training arguments here, right? So we have this args input, and I'm going to set my training arguments. So again, I already imported the training arguments from Hugging Face, if you remember, right? So since we have 2 GPUs, the first one is per device train batch size, right? So I've set it to 2. Right, so this is a number of examples processed per device GPU at a time, right? So per device train batch size. Gradient accumulation steps, so equals 4, right? So here, again, this is how many steps the gradient needs to accumulate before updating weights. So essentially, how many steps does the training process needs to take to a certain extent, if I'm explaining the intuition here, before we update a weight, right? Number of training epochs, I'm going to set this to 1 so that we specify this a full fine-tune run, right? Warm-up steps, so how many equals 5. So we're going to essentially gradually increase the learning rate for the first 5 steps, right? Max steps, so how many steps in the training process is a maximum? So 60. I'm going to set this here, right? Learning rate, I also, this is also kind of canonical here. I'm going to paste this here. So this is, I think, 0.0002, if I'm not mistaken, right? And then, again, these are all arguments that I recommend that you check out the documentation from Hugging Face to be able to get a better idea. But again, intuitively speaking, what we're just doing is updating the model weights, and we're defining a few of these parameters that let us do this effectively. So other functions here that I'm going to, the arguments that I'm using, FP16, so this is float point 16, right? And given that we, so here it would be to use float point 16 if bfloat 16 is not supported to speed up the training. So I'm going to do not is bfloat 16 supported. And then bf16 equals is bfloat 16 supported in case we have support here. Logging steps equals 10. So logs the training progress every 10 steps here, right? What is the optimizer that we're going to be using? So we're going to be using the Adam WB 8-bit optimizer. Oops, we need to add here. Weight decay equals 0.01. And essentially here, what this does is to, it allows regularization to provide, to prevent overfitting. So what this does is as well, like just avoids the model to overfit on the data set and becomes inaccurate on other tasks, essentially, or just becomes only accurate on the training data. So what is the type of learning rate that we're going to set? We're going to set it to linear. Again, these are all technicalities about the training process and fine-tuning process. My objective is to provide you intuition here. And then seed, I'm going to set it as well to 3407, just so we can have a random seed for reproducibility. And the output directory, I'm going to set it to outputs. Okay. So I think this is it. This should be correct. Ooh, we have a mistake on the LR scheduler type. Ooh, this is LR scheduler type. Okay. I think we're good to go here, right? And now the process is to train the model, right? So we just need to train it, and all you need to do is do trainer stats equals trainer dot train. And I'm not going to run it here because, and then what we want to do as well is use the weights and biases function to finish the fine-tuning process, right? And I'm not going to run it here because it's going to take 30 to 40 minutes, but I do have the already solution that you can see here, right? Now, as you can see, we've defined those 60 steps that you can see here. So the model took 60 steps. It did 60 iterations on the fine-tuning, and it logged the performance every 10 steps, as you can see here. And we see that the training loss went down, which is good to see. And then we ran the weights and bias experiment and finished it, right? And then we did get this run history and then run summary. And then we did say, if you want to view your project, you can see it right here. So I go to my fine-tuning process, and as you can see, my loss function is going down, which is good to see, right? And then now all I need to do is test out my fine-tuned model. So going back here, I'm not going to run the code here, but going through the same exact process, all what I'm doing is I'm loading the inference model, which is model LoRA, right? Since we fine-tuned that model, as you can see here, right? And then we're going to generate some output tokens, right? So the first question is the same question we asked before fine-tuning. We see a much shorter chain of thought than before. And then the format, as you can see, 3 sentences or 3 lines, much shorter as well than the previous one. Now, I also got another question here that you can see, 59-year-old man with fevers, chills, so on and so forth, right? And as you can see, much shorter chain of thought and a much shorter answer as well. Now, here, this example, right, is fine-tuning on a medical data set, but you can really depend on the data sets that you find on Hugging Face, fine-tune your model on almost anything. And that's it for today's tutorial. And whether DeepSeek ends up being a fad or all smoke and mirrors, I think it's up to be seen. But what is undeniable is that you have a pretty strong reasoning model that you can fine-tune today on your own datasets. In a lot of ways, this is still the beginning as AI systems continuously improve, and whatever tool you build or application you build, make sure you build it in a model agnostic way, because you don't know what the next best model will be or the most cheap model will be. And with that, I think this is a great place to wrap it up today. We left a bunch of resources in the description, a lot of explanations on some of those technical terms that we weren't able to explain. But with that, have a great day and happy learning.